So I think the arithmetic on matrices is quite different when it comes to multiplication. Personally. So are we ready for some formal definitions? I don't even remember if I gave you guys a formal definitions yesterday. Linear dependence and independence?
Sure.
You did it 2 days ago.
I did.
Could you
That's right. We got off the track yesterday.
can you just like quickly refresh us?
Absolutely. Good definition. Reset. Of vectors.
Oh, that's right.
In a vector space. Is said to be number one, linearly independent. If when I have a linear combination of these n vectors, being set equal to 0 bar, the 0 vector, then it necessarily means that all the CI's are equal to 0. And I will say that a set of vectors up here is said to be linearly dependent. If linear combination is equal to 0 vector, where not all of the C's. In other words, I can find some C's, not all of which are 0, for which this linear combination is equal to 0 vector. So let's talk about some special examples. I'm assuming I had a vector from a vector space. Is this set linearly dependent or independent?
It's dependent because you could have a scalar that is not 0, but the vector could be 0 bar.
So you're saying no matter what v bar is, I can multiply it by c, and that product will be the 0 vector?
I'm not saying that. I'm
Okay.
saying that there is a way to set a linear combination c times v bar equal to 0 bar, and for that to not necessarily imply that c is 0.
And I think c is not going to be 0 only if v bar is
0.
the 0 vector. Thank you. Good. So I think the single set is going to be linearly
Dependent.
dependent if v bar is the 0 bar. I agree. And it's going to be independent otherwise.
But I have a question.
Sure.
What is it dependent on?
What's that?
What's it dependent on?
It's not, I'm not using the word dependent in that fashion anymore. I think with my definition, my version of dependence is this. If I got these things, a lot of them, in this case just one, the v bar. If I force c times it to be equal to 0 vector, and that forces c to be 0, I would say that that set, containing that single item, is going to be linearly independent. And I think c times a vector v bar is going to be equal to 0 vector is going to be a true statement when v bar is not the 0 vector, only c is equal to 0. And so I think it forces my linear independence. What about this one? I've asked you this question, I think, already. You just give me the answer. That set was literally dependent because I can build a relationship. I can find constants C1, C2, C3, not all of which are 0, for which the linear combination of these three beats is equal to 0 function. Because 0 is a function. And when it came to this example, linearly dependent for a similar reason. Namely, to some of these two pieces, nothing more than
Pi over 2.
pi over 2, yes, got it, good. Have we talked about linear independence and dependence? I get the feeling we did. It's just been 2 days, I don't remember.
We touched up on this a bit
But
yesterday.
it's only a little bit.
Just for like 5 minutes.
All right, my apologies. I'm not remembering well.
So, yeah, if you just scaled both of those by -2, they'd be the
So
same
what's your
exact
answer?
line.
Independent or dependent?
Linearly independent, or linearly dependent.
I think this set is a linearly dependent set of elements in R2, clearly because one item is a multiple of the other. After all, if I've got this one vector v2 bar being equal to -3 times my v1 bar, doesn't that necessarily imply that 3v1 bar plus v2 bar is equal to 0 vector? So whenever I have a set of 2 elements and one item is a multiple of the other, clearly there's going to be linear dependence with the set for the same darn reason. I can find non-zero coefficients, namely 3 and 1, for which that linear combination is equal to 0 vector. What about this set?
Independent.
No, it's dependent.
Why?
I just feel like it is.
Yeah, it's sort of like just 2 elements, two I can't speak today, 2 linearly independent elements are going to generate all of our 2. Oh shoot, I threw an extra one in there. I think for free I can express it as a linear combination of these 2. Treat these as standard vectors back in R2, like back in Math 8, trigonometry. Is it not true that 2 vectors span all of R2?
Mhm.
Which means any third vector can be expressed as a linear combination of the first 2 that I just gave you. I think clearly this is a linearly dependent set. If you don't like the way I'm talking, we can prove it.
Yeah.
To prove it, let me force the linear combination of these 3 elements. To be equal to 0 vector. And now equating coefficients, don't I generate these equations? 2c1 plus 3c2 is equal to 0. Oh, I misspoke, didn't I? Jeepers, I missed one. I meant plus 8c3 is equal to 0. But also equating the second components. 3c1 plus 4c2 plus 29c3 is going to be equal to 0 as well. Now, if I draw for myself a nifty little augmented matrix and try to find the values for C1, C2, and C3, here's what I get. 2, 3, 8, 0. 3, 4, 29. 0. Now manipulating. So give me a 1, 3 halves, 4, 0. And then I generate, I'll keep the 3, 4, I should say, 29 and 0. Continuing with my process of Gauss-Jordan elimination, let me just operate on the very second row. I think it generates this. And then I can write this. Or shall I say finally, this. I said this, I gotta slow down. Jeepers, -3 halves. What's that?
Aren't you missing something there?
Yes, I am. That's why I'm stalling. I'm trying to do the arithmetic in my head. And look what this says in the board, you guys. Look at the augmented matrix. It says the following. It says C1 is equal to -51 C3.
I was trying to do it. I
And
couldn't do it.
C2 is equal to 34 C3. Can I make up a number out there for C3? 1. If C3 is equal to 1, that means C1 is -51, C2 is 34. Jeepers, I just found 3 non-zero constants for which that linear combination is equal to 0 vector. So I just proved to you that set has to be linearly dependent. Ooh, you didn't like that. Okay. the word solution. It's just you're talking about solutions to this equation, and you're looking at solutions for C1, C2, and C3. So I just think another way of saying that is I've got infinite collection of values for C1, C2, C3, for which that linear combination could be equal to zero vector. Linear dependence just simply says this. If you can find some non-zero costs in C1 through C3, for which that linear combination is a zero vector, you have linear dependence. Are you guys with me? You don't think so? That was fast.
But, I mean, think is not really a specific term.
So how do we find out? We make a matrix, or before you get there, how about saying this in English? To
So-
find out if it's linear independent or dependent, we'll just look at a linear combination. Force it to be equal to zero vector in this vector space. And if I'm solving for those coefficients, they all end up being zero, then I know my set's linearly independent. If when I force a linear combination of these elements in P2 to be equal to zero, and I find out that I can have some values C1 through C3, like this example, that are not all zero, well then I know my set's linearly dependent. Let's give it a shot. In giving it a shot, I am going to, well, just equate. And if I equate coefficients, wouldn't that give me this? Be honest with me if I'm skipping too much work. Be honest with me.
Can you explain how you got that?
Yes,
Well, let's see.
I was equating coefficients. So I was basically taking,
Why'd you do it in some weird order, though? That's because it looks like you started with your third term, then you did your second, then you did your or your first, and then you did your second.
you're the one making me do all the work. And so if I'm going to reduce this matrix, I was just selectively placing that one first.
Oh, the top one.
Because you make me do all the rest.
All right.
I think where this matrix comes from is this. C1 times one of those elements. Excuse me, that's not it. Plus C2 times this element. Plus C3 times this element. If I force this to be the zero element, P2, then I think it simply forces the constant term, which is C1 plus 2C2 plus 3C3, to be equal to zero. I think it forces the coefficient of x on the left-hand side, that's C1 plus 2C, that's C1 plus C2, and no C3s, to be equal to the coefficient on the right-hand side of x. Well, there isn't one, so it's just zero. And finally, equated coefficients of x squared. It's just that when I sit down and reduce this matrix, oh jeepers, you guys, we better crank this out. I made this example up out of thin air, I really did. So maybe yes, maybe no. We'll find out. Is that a 0? -1, -3 is 0. Is that a 0, -4, -7, 0? But that's going to give me this equivalent augmented matrix. Yeah. Is that a 0, 1, 3? Or shall I say, I get 1, 0 something, 0, 1, 3, comma, 0, and then 0, 0 something. Let's talk about the somethings. I think the first something is going to clearly be -3. Did you see what I just did? I said -3, but don't look what I write, just look what I said. And I think the second something is going to be the positive 5. But now, massaging this further, jeepers. Isn't that pretty? What does it say? says C1 is 0, C2 is 0, C3 is 0. So when I was assuming I got a linear combination of these three vectors set equal to the 0 vector in P2, and dealt with finding what the C of some i's are, and found that they had to be equal to 0, then I think I've got linear independence. Chris?
How did you jump to the final identity matrix? Just questioning your raw operations here.
In my head, I did this. Dividing by 5, piece of cake. But I knew with 1 here, I could multiply by anything in Dermo please and get rid of these, because it doesn't affect any other columns.
So you're doing
I-
just row 1 and 2.
I think it's for free. Again, I'm being lazy.
So does that mean that if that were to be like a spanning set, would it be efficient, or are we just?
What
is
a
that
nice
totally
thing to put in
different?
there. Since I want to generate P3, I think I need 3 elements. But I don't want more than 3 elements. And to generate P3, all I need is any set of 3 elements from P3 that's linearly independent. So I think this spans all of it. Sorry, did I say P3?
Yeah.
My apologies, I meant P2. I have to really watch what I say in this class. I think the author's horrible in referring to vector space as P2. I do call it P3 for myself. I try not to say that in class. I like calling it P3 because I think I need 3 elements in a spanning set. You guys forget rid of anybody else?
This set is linear.
So this set is literally independent.
Something like P3 or maybe R3.
R4.
It's called P2 and R3.
Okay, gotcha.
For something like that, is it possible to find a spanning set with only 2 elements?
No, I'll need at least 3 elements for those 2 sets, for those 2 vector spaces.
Okay, so just to sum up, so after we, I guess, build a system of equations and then do row operations. So the thing that's important to look for is whether C1 through however many C's there are is all equal to 0 or all equal to some combination of the other terms.
If the C sub I are all 0, or maybe the sum of the C sub i's are not 0. That's the question you're asking.
Okay.
If they're all equal to 0, independent. If when you solve for them, the C sub i's, I found some of them, at least some of them are not 0, then you got dependence. So, Chris asked this. Let x1, x2, and x3. I think I said that incorrectly. Let the order triplet x1, x2, x3, and the order triplet y1, y2, y3 be in R3. Does this set right here span all of R3? That's a good question. To answer it, let me just simply take a linear combination of these 2 beasts. And set it equal to 0. And again, I think in setting this linear combination equal to 0 in R3, if I can prove to you that C1 and C2 are equal to 0, I've proven to you that this set is linearly independent. But if I can find some values of C1 and C2 that are not 0, when I assume this, then I think I've shown you that I've got a linearly dependent set. So let's just run with it. Can I cheat with an augmented matrix? Because it's easy. And cheating with an augmented matrix, cheapers, what does that give me? Does that give me x1, x, I misspoke, y1, 0? Gives me an x2, y2, 0, as well as an x3, y3, 0. In reducing? Okay, I'll need more room than this.
Before you continue,
Yes?
I don't think you really explained to anyone the relationship between span and linear independence or dependence. So I'm confused as to why we're looking for independence.
You might haven't tied it together. Yeah, because I think I can have a spanning set that's linearly dependent. And I can have a linearly independent set that doesn't span all of my vector space. So the way I'm going to tie these together, which is today, not in the distant future, is I'm going to say, if I want an efficient spanning set, a spanning set that doesn't have extra stuff in it, then I'll consider such a spanning set to be linearly independent. And if I have a linearly independent spanning set for a vector space, I'll give it a name. I'll call it a basis. As a matter of fact, if I find a basis for a vector space that is, again, a linearly independent spanning set, then I might even say, well, the number of elements in that basis is going to be what I refer to as a dimension of my vector space. That's how I'm going to tie these two notions up really, really well. And so it really culminates when we're discussing bases. But you guys, this is a good question. Let's answer it. So I've got a 1, y1 over x1, 0. Excuse me. What do you mean?
Because you're using x1 to cancel out x2, subscript 2.
No, in my head. When I look up here, I'm imagining this line replaced with this one. If you trust my operations.
Yeah.
And next, I think it's going to give me this. You guys agree so far? You don't want to play anymore.
I just, what row operation did you use there to get the one?
It was this easy. Combine these to a single fraction by finding a common denominator.
Okay.
And then multiply that row by its reciprocal. It's gone.
So technically, when it's set up like that, if we just put a 1 there, you wouldn't know the difference, would you?
I'd be unhappy if you didn't put a 1 there.
Yeah, but if, say, we didn't explain the row operation and we just said, yeah, we just multiplied row 2 by whatever we needed to.
I think it's true.
Okay,
That that's gonna
all
be
right.
1. Just take whatever it is and divide by itself, and you're going to get 1.
Okay,
But you guys agree?
yeah.
Oh, wait.
I'll wait.
1 equals 0?
What about it?
No, that's not, okay.
All this is going to say is that one of my coefficients is 0.
Oh, okay.
So it's linearly independent?
What's that? I'm sorry, I missed it.
It's literally dependent.
Well, it would be independent, wouldn't it?
You know what, you guys? I'm stalling. Chris, I'm wondering if I forgot what the question was. I didn't do anything wrong on the board. There's no mathematical errors with
That's
that.
why I
Well, you asked if it spans all of R3.
Yeah,
Um,
Well, it's
gotcha. And I did not
So,
answer that question. I think I really flubbed up, not with my math, but I just answered the question, are those two things linearly independent? Assuming x1, x2, assuming they're different values. But I have not answered your question. I think to answer your question, I need to do this. I need to imagine this linear combination of these two elements to be an arbitrary element in R3. How about z's? I think I gotta change these. I think it changes these. I think it forces this.
I was expecting you just to do the math really fast.
Do you know what? These things are non-zero.
Yeah.
But that kind of suggests that 0 is equal to that non-zero real number, which is a logical contradiction.
How do you know Z3 is 0? Or non-zero?
I think it's for free. Because I think when I apply these elementary operations, it's just going to change these values. It's not going to drop out. There are no additive inverses in here. I'm going to get an expression involving Z1, Z2, and or Z3. And I admit sometimes it's going to be 0, but not for all values. And I'm trying to imagine any element in R3 expressed in a linear combination this way. And I know it's true for some, but not for all of them. Because I get a non-zero real number over here, I get an expression for Z1, Z2, and Z3. This time I did cheat. To answer this question, I really did cheat. I didn't finish the work. I used my quotation marks. But if I did finish, they would be non-zero real numbers.
So if you're just trying to figure out if there was a element in R3 or a element
In R3,
out of those that spans R3, then you just set whatever that third term was equal to 0, and then you would.
no, I'm not sure
find
I
your
understood
values?
that question.
Okay.
So start from scratch again.
So say that you went through the whole process, right? You have your final term, which is happy face plus smiley face equals
Yes.
0.
Yes.
Then you would take, and if you were looking for like a value of x comma 1, x comma 2, x comma 3, y,
I
all
see.
that stuff that is in R3, then you would just take that and you would find your possible coefficients.
Yeah, I agree.
Okay.
I don't think it's a very useful question, but yes.
On the test, would you be asking us something like this, except asking us to find where it does, if there's anywhere where it does span on 3?
Yeah.
Like a subspace that.
But I think on tomorrow's test, I can already ask you that question. Because I think what you're saying is, can I find what space my span set generates? Absolutely, yes.
So, Professor?
Yes,
so
sir.
when you have 0 equal to a non-zero number on the bottom, like, isn't that a problem? What are you supposed to do with that?
You know, it's not really that this is a real number. It's that this is going to be an expression in terms of Z1s and Z2s and Z3s.
Yeah, but you said it's non-zero, right? So,
So if I get an expression like that,
okay.
since this isn't equal to 0 for all possible points of Z1, Z2, and Z3, then I think I've got linear dependence. I misspoke, didn't I? I said linear dependence again. I meant I do not generate all of R3. Because think about it, Chris, watch. I know I lied with what I put in red, but what that last row of the matrix really says is this: that 0 is equal to Z1, Z2, minus Z3. That's what it really says, isn't it? But that means Z3 has to have the quality that, oh, look at this. They can be expressed as a combination or a product of Z1, Z2. That means that the only vectors in R3 that this set spans are those that have the quality that whatever this Z component is the product of the X and Y components. That's one heck of a restriction, isn't it? That means my original set, no matter what these are, does not generate an arbitrary element R3. This set does not generate all of R3. It only generates a restriction of R3 where this particular entry is the product of these two. I think that's why that last row, Chris says, that I've got that I do not generate all of R3. Does that make sense? Well, sometimes I don't have to go through all this work.
Excellent segue.
Yes, it is. Actually, speaking of that, can you guys just give me that most previous example? What was the example for this one? Example number 6.
Is that the one in P2?
Yeah, so what was that set of elements?
2 plus x, 3 minus x squared, 1 plus x plus 2x squared.
There's another way to verify linear independence. I can compute what I refer to as the Wronskian. Wronskian is nothing more than a determinant. And this example is going to be a 3 by 3 determinant.
Can you explain the origin of the term Wronskian?
Yes, it's from a
what's Wronskian.
His name, I believe, was Wronski, so W-R-O-N-S-K-I. But I don't know anything about this particular individual, I really don't.
Okay.
I don't ever remember coming across him.
He wasn't one of the ones that was killed, was he?
Well, at least not in an interesting fashion.
Not in an interesting way. All right.
There were some really interesting deaths in mathematics.
Yeah.
Especially during the Inquisition. Or no, not the Inquisition, but
Yeah, yeah, that had problem with actually some science.
yeah.
What's the most interesting death in that? Just one.
Archimedes.
Archimedes had an interesting death. He single-handedly defended the island of Syracuse for years from Marcellus, who was running the Roman fleet at the time, who conquered everything in the basic Mediterranean area. One day, Archimedes was sitting on the floor doing a problem, working something out. And since he wasn't defending the beach, then the Roman fleet came in. They went to the community. They had very specific instructions. Kill whoever you want. Don't touch this guy. We're going to bring him back to Rome, and we're going to treat him like a hero. Because he fended off the Roman fleet in so many different ways using math and science. That the Roman Empire just thought he was a genius. They knew he was a genius.
They wanted him.
No, they didn't want to abuse him. They just wanted to treat him like royalty.
That's what I'm saying. They wanted him to help them now.
Perhaps. And so one day, the Roman fleet they saw nobody fending off the city or the beaches. They embarked and went to town of Syracuse, and they found him. One of the soldiers didn't know who he was. He was just sitting on the floor doing some mathematics. And he came to Archimedes from behind and said, "Get up," and repeated himself a couple of times. And Archimedes kept saying, "Get away from me, I'm in the middle of a math question." And so the soldier apparently just took his sword, chopped his head. Pythagoras had an interesting death, but we're in mixed company, so I don't want to get into that. You can check that
I
out.
heard it was something with beans, actually.
Yeah, it's a whole bean thing, yeah.
Really? It's true? That's not just urban legend?
I'm gonna look this up.
Pythagoras was a real nut. I mean, he thought numbers had magical qualities. He thought some numbers had masculine, feminine qualities. They were feminine numbers, masculine numbers. He had this very weird belief that beans you should never step on because they're in the shape of a part of the male body. And so you never step on beans. And it got to the point where he was so abusive to the community in terms of insults that they came to his house and they burned it down. And he started running. And they ran after him. And he happened to be running into a bean field. And he refused to proceed, and so they caught up with him and killed him. You ever heard about the guy, one of the members of the Pythagorean Society, who measured the length of a diagonal of a square and say these are the lengths of sides? The length of the diagonal is √2. At this point in history, this is pretty early in Greek history. The Greeks believed that all numbers were commensurable, meaning no matter what two numbers you have, you can always find a smaller number for which a multiple of it is going to be these two numbers. What it really amounts to is assuming that all numbers are rational. It means the same thing. And one day, one of the members of society was messing around with measurements like this, and he discovered that that number has to be irrational, non-commensurable. But at this point in time, the Pythagoreans had already grabbed a lot of theorems and put proofs to them and verified them. And one of their assumptions in all those proofs is that all numbers are irrational. Well, he came back and told the other members of society, and they just kind of looked at each other. What do? We tell everybody in society we're wrong, or we shut this guy up? So, as one story goes, they tied him up, put him in a boat, sent him out to the Mediterranean, dumped him off, so nobody can find out. But everybody else eventually found out. Excuse me. Do you guys remember high school geometry? Do you remember all the algebra and the arithmetic in that class in high school geometry with all the Greeks? Do you?
No,
What do you mean, no, why not?
because I didn't take geometry in high school. I
Oh,
took
that's
it in
why, okay.
junior high. And
I was hoping you all say, no, you don't remember it. Because when you were in high school geometry, you were learning what the Greeks did, and it was all geometry. That's why. They were so pissed off. They were so upset. They said, this doesn't make any sense when everybody finally find out. And they said, we're not going to study any more arithmetic or algebra in our society because it just doesn't make any sense. Let's just stick with geometry. That's why all the body of material is geometry. You heard of Galois?
Yeah, French guy,
Yeah, the French guy.
the one who died.
It's okay. Galois was he was very much of a political dissident, and the new government coming in after the government took over France, after their revolution. Thank you, took over. Galois was a really strange character. He did not like authority at all. At one time, he tried to get into the Polytechnical University in Paris, which at the time was the greatest university you can go to, particularly in France. And he sat down and took the incoming test, the entrance exam, and is in a room with people, the students, and the professors up front who administer tests. And he just looked at the exam and thought it was so stupid. How can these universities let students in who can pass this exam? Because anybody can pass this exam, so he thought. And he got so annoyed, he just took his eraser and just beamed it across the room. Hit the professor right between the eyes. It was an absolute guarantee he would never make it in that university. But he was very much a nerd. And one day, a woman gave him some attention, and some things transpired, and then very soon afterwards, he got in an argument with somebody in a bar at the time. And those two said to each other, okay, tomorrow morning, we'll show up here with guns. We're having a duel over this girl. Now, some believe in history that the girl was a setup. She really had no interest in him. It's just that one way the government tricked him to have a duel with somebody so they just kill him because it was tired of his dissident behavior. And so Galois, he had never written anything in mathematics. And we're talking one day, he's in this bar-type situation, and he's got to go home, and he's thinking, you know, I'm a mathematician. I know I'm going to die because I can't fight this guy. I don't have no skills. And so he had to sit down that night and write everything he had in his head in one night. Went out the next morning, and of course was killed in a duel. So it's a thing called Galois theory. He had to put down in one night. That was his one. Previous to that, he would send papers to some professors in France, but they wouldn't listen to him. These are the interesting ones I can think of. You heard?
There's Socrates too. Right?
Socrates, yeah, Alan Turing. Alan Turing was an interesting death. You know who Alan Turing is? I think there are two mathematical reasons why we won the Second World War. Now, this is definitely one of them. I just talked about the
Oh
ellipse.
God, is this the guy who cracked Enigma?
He did. The Enigma code was, the Germans had a code for the U-boats that we just couldn't tackle. The British government hired Alan Turing to devise a scheme to decode these machines, and he succeeded, and single-handedly changed the direction of the war. But he was a homosexual. And so after the war, the government found out, the British government, and they chemically castrated him. And he was so upset about this being drug out in the public, he decided to take his own life. So Alan Turing killed himself. So the gentleman single-handedly saved the entire Allied forces, took his own life because he's too embarrassed by what the government was doing. Pretty nasty stuff. And he is truly the first person to come up with a solid computer. We consider it the first modern computer. You know, what's really interesting about his death, though, is after he died, his family scurried into his office. They grabbed all his papers and took them home. And they looked at some of them. They were embarrassed by the papers, the mathematical papers. And so they kept hidden. Till somewhere in the 90s, the families finally decided to let these papers out. And these papers written like in the late 40s, very early 50s. And some of these papers, he was talking about biological computing. So using biological material for computation purposes. And nobody had even thought about it before. And I haven't heard anything since. It'd be really interesting to see if anybody's done any work in that area. I'm not a biologist, so I don't know. But biological computing could change computers completely. Potentially, I can see how it can do it.
Right, it's off to get another laptop.
They did it for data storage.
Have they done that for data storage?
Yes, they have.
Petabytes of data in like the squares
Wow,
computer.
that's
They use
interesting. I gotta check it out sometime.
they use DNA and basically use it as binary code.
Wow. I'll have to do some reading on that. It sounds like it'd be fascinating. I just don't know.
I know video.
You've got a video?
Well, kinda. He the guy who made the video, he doesn't usually cover that, or this sort of stuff, but he covers video games mostly.
Gotcha.
But it was the subject in a video game.
So you guys, where am I next? Oh shoot, I forgot the Wronskian. Sorry.
We have to review the exam. We got half an hour.
Oh, we reviewed yesterday. So what was that said again? It was 2 plus x?
Yeah, 2 plus x.
Sorry, you guys.
3 minus x squared.
And
1 plus x plus 2x squared.
2x squared. An alternative way is to compute the Wronskian. Is the 3 by 3 determinant, where the first row simply contains my 3 vectors. Now this technique's only going to work if your vectors are actually functions. Because the next row are going to be their derivatives. The third row are going to be their second derivatives. Now, if I already compute this Wronskian, how about doing it by expanding about, how about the third row? Wouldn't that give me a positive 2 times, I don't know, is that an h plus 4x? No, it's not. It's the product of 2 plus x and 1 plus 4x. Minus the product of, or how about just minus the quantity, 1 plus x plus 2x squared. Plus 4 times my, is that a negative 4x minus 2x squared